This is the Triaxial test setup, which allows you to conduct unconsolidated undrained, consolidated undrained, and consolidated drained tests. This is UTEST multiplex universal electromechanical machine, which has Triaxial cell mounted on it. And this is a constant pressure unit, which is connected to the cell, and this is another constant pressure unit, same with the other one. And this is the volume change device, which measures the water volume that goes in or out into the specimen. We also have a deairing tank in order to use the deaired water into the test while doing the tests. And we have a vacuum panel over here, which makes the water inside the tank be aerated. We have a data logger, which collects the data from the LVDTs, pressure transducers, over the system, and gathers them and sends these data to the computer software program. The constant pressure unit has a power inlet on the right side and power on and off button just above the power inlet. We also have a stop and stop button which initiates the machine and stops it. We also have a pressure control knob over here. We can, while we are turning it the clockwise direction, it increases the pressure. While returning it on the counterclockwise direction, the pressure is decreased. This is just to maintain a constant pressure before giving it to the cell or inside of the specimen. And we also have a dump knob over here. In case of an emergency or when it required, when you pull this knob on this direction, it just releases the pressure inside of the oil tank again, and pressure becomes zero. This is the volume change device. It is connected to the constant pressure unit again. It is used with the water which is fed into the specimen. It is important to determine how many water is go inside of the specimen or outside of the specimen. It has a cylindrical piston cylinder assembly which has a LVDT unit on it to measure this vertical displacement, and by the program it calculates the volume change of total volume change. It has a flow up and flow down knob on it, which allows the water flows from downside to upside or upside from the downside. It has a, again, volume change or bypass knob. On the bypass mode, the water which is fed from the constant pressure unit is directly goes inside the specimen. If we choose the volume change, the water again goes from the volume change device and then goes to the specimen again, which makes us possible to determine measure the water amount. Let us start with the assemblage of the system. The aeration water tank has two outlets. One of them is connected to the constant pressure unit inlet, and the other line is connected to the other constant pressure unit inlet over here. Actually, this constant pressure unit is directly connected. The outlet of the constant pressure unit is directly connected to the cell pressure of the triaxial cell and creates a chamber pressure inside the cell. And the other one has an outlet to the volume change device, and outlet of the volume change device is connected to the back pressure, which feeds the specimen with water from the top cap. And this is the pore pressure measurement branch, which is connected to the nowhere. And this is the multiplex machine, which has the triaxial cell mounted on it. The triaxial cell has a piston to transduce the force to the specimen vertically. And this piston is connected to a S-type pressure load cell, which has a 500 kg of load capacity. The triaxial cell has 3 pressure transducers mounted on it, and it will be connected to the load data logger afterwards. This is the pore pressure. This is the pore pressure transducer. One of the veins which connects it to the cell is opened all the time, and the other one is always closed. This is just for the measurement of the pore pressure of the specimen inside. And this is cell pressure measuring transducer. And while during the test, both veins are opened. And finally, the last transducer is to measure the pressure inside of the specimen, which is called back pressure. And this is also opened during the CU and CD tests, which is not necessary for UU tests. And we have also linear variable displacement transducer, which is called the LVDT shortly, mounted on the device, which makes possible to measure the vertical displacement of the specimen. This load cell and the LVDT is directly connected to the multiplex machine from the backside. These load cell and LVDT communicates with the machine, and while conducting the test, it determines how the speed and the load values to the machine. Here we have on the multiplex machine, we have an emergency start and stop button. Now we are opening the device. This is the PC100 TFT unit, which makes us easier to select the test parameters, specimen dimensions, and so on. The test can also be started and stopped from using this TFT screen, as well as the program on the computer. After the screen has opened, we have 3 selections. One of them is CBR, the other one is Marshall, and the last one is the Triaxial tests. We are choosing the Triaxial here. Now we have specimen settings menu, test parameters, test selection, device settings, decimal points, test results, and test screen. The first menu on the screen is specimen settings. Since we have used the 50 mm diameter of specimen, we are going to enter this diameter as 50 mm. And the height of our specimen is 100 mm. As you can see, the area is calculated automatically. And assuming that this is the first test, we are entering the first lab number 1. And by entering OK, we are out of this menu. The second menu is test parameters. The first option shows us the test number. We are entering the first test. And the second one is maximum load. And the third one is maximum displacement. And the fourth one is the failure threshold. And the failure detection is set as 10%. Here we have test speed. The speed is selected as 0.5 or any other speed that is necessary on the shearing operation. It can be determined by some calculations or the related standards, but for now we are choosing as 0.5 millimeters per minute and pressing OK. Displacement tear, which makes us to set displacement as 0, and maximum graphic displacement and maximum graphic load. The third option is the test selection. As you can see, you can select CBR, Marshall or Triaxial. Since we are going to conduct the Triaxial testing, we already initially selected the Triaxial. And the fourth one is device settings. Here in the general tab, you can set the time and the date and the language. And the second tab is units. It is initially selected as SI unit system, which is metric system. And the other menus are load displacement, load decimal points, stress decimal points, and displacement decimal points, which are necessary significant figures that have to be selected before test. And here is the graph settings. You can change the color of titles, axes, graphs, and the grid lines and so on, while using this menu and the color buttons over here. The sixth menu is the test results menu. It is not necessary to enter any value over here, because according to our specimen settings and the related values, these will be automatically shown up on the test report. And the last one is the last important one is the test screen. This is the test screen. After entering all the required values about the specimen and the speed and so on, we can manipulate the test or initiate the test from this menu. Here you can see maximum stress, speed set as 0.5 millimeters per minute, load and displacement, and test start time and test end time. Here you can read the loading and the displacement over here. The first button of the 6 over here is tear load, which sets the initial load as 0. Second one is tear displacement, which sets the initial displacement to 0. And the third button initiates the test. And the fourth one stops the test. And the fifth one resets the value. And the last one goes to the main menu. I'm going to show just a representation. At this speed, at these confinement pressures, for example, we can initiate the test. And you can see the load increasing and the displacement. Now I'm stopping. And while resetting it, we are now turned to the initial values. Here on this table we have all the tools that we need to assemble a triaxial cell with the specimen inside it. Here we have a triaxial cell pedestal, the top cap with the drainage tube, and the triaxial cell upper part, fixing screws. We have O-ring placing apparatus and O-rings, 2 porous stones, 2 filter papers, and membrane placing apparatus, split molds to prepare disturbed specimens, and a cutter in order to cut the undisturbed specimens from the blocks. And we have a pre-made specimen over here. Now we are going to assemble the triaxial cell. We are starting to place 1 porous stone at the very bottom of the pedestal, and then the 1 filter paper on it. And our solid specimen. And filter paper again, and at the very top, 1 porous stone. Now we have a membrane dressed on the membrane placing apparatus, and we are creating a suction inside of it for the ease of placing the membrane. After placing the membrane placement tool, we are wearing the membrane around the specimen. And again, the other one on the bottom of the specimen and over the pedestal. After the membrane is correctly placed, we are removing the membrane placement tool. Now we are going to place the O-rings on the bottom of the pedestal by using the O-ring placing tool. First we are going to wear O-rings around the O-ring placement apparatus, which is a little bit tough. We are going to use 2 O-rings at the bottom and 2 at the top. Now we are going through at the very top and placing the O-rings. Now again the same procedure for the upper part of the specimen and the top cap. Alright, we are removing the drainage tube on the top cap and we are placing the top cap inside of the membrane, and we are placing the O-rings at the top of the specimen and around the top cap. Okay. Now we are, before connecting the tube, we are just making counter dressing to the membrane. And we are finally connecting the drainage back pressure tube. Okay. Now we are going to combine these 2 parts of the triaxial system. And finally we are connecting the fixing holes. we are being sure that the fixing rods are tight enough in order to fix and hold all the system together. Now we are going to place the triaxial cell on the top of the multiplex machine. After using the screws, we are just centering the piston with the load cell. After arrangement is done, we are locking the cross beam over here. Now we are going to place the LVDT. Now it's fixed and free to move. After placing the LVDT, we are going to fill the chamber with the water. In order to do that, we are going to use the aerized water inside of this tank via on this unit. We are going to connect this tube to the chamber pressure inlet, and we are going to first open these valves, and we are going to open the valves on the unit, and finally we are going to open the valves of the chamber pressure and letting the water rush into the triaxial chamber. While we are doing that, we have to be sure that the air bleeding valve should be open in order to let the air go outside freely. And we are going to wait until the chamber is filled and there is no air bubbles left inside. As you can see, our triaxial chamber is filled with water fully. There is no air bubbles left inside. And it's ready to go another step. In order to complete the unconsolidated undrained test, which is called UU, we are going to test 3 specimens, one after another, and at different chamber pressures to draw 3 more circles and a more envelope, which is tangent to those 3 more circles. Now we have assembled our triaxial chamber on top of the multiplex universal testing machine. We have arranged the screws and cross beams for load cell and piston just to touch, and they are all centered. Now on the test screen, we are going to choose test parameters, and we are going to choose a predetermined compression speed on the shear stage. Let us choose 1 millimeters per minute. It is okay now. On the test screen, you can see the speed as 1 millimeters per minute. We are going to tear and reset the load as 0 and tear the displacement. Now, we are going to create a chamber pressure inside the triaxial chamber while using this constant pressure unit. We are going to use this comparator watch to just determine the chamber pressure and stabilize the pressure inside the chamber. And then we are going to go to the program. On the UU software, we are going to create a new folder. Let's say UU. On the general information tab, we have some boxes that you can fill. First one is laboratory number, project name, well known, date, sample type, sample shape. On the right side, test standard, sample accept date, test start date, test finish date, used sieve, tester and controller. These are the values that is going to be presented in the final report. If you enter these values after the test is completed, they are all going to appear in the final report. Now the first tab on the left side is the graphics information. On the right side there is some boxes that needs to be filled, about the specimen. Again, we have used 50 millimeters diameters sample, and which has a height of 100 millimeters. That's why we are entering 100 millimeters on the sample height, 50 millimeters diameter, and as you can see, area and the volume is automatically calculated. And the other boxes just show the calculated values, for example, strain, area, deviatoric stress, sigma 1 minus sigma 3, and so on. On the upper box, we have sample number that changes. For example, sample number 2, 3. Since this is the first sample that we are going to test, I have chosen the first sample. Here, sigma 3 in kilopascals, which corresponds to the chamber pressure. You can set any value, for example, 50 kilopascals, 100 kilopascals and 200 kilopascals, or 100 kilopascals, 200 kilopascals and 400 kilopascals. Let's start with 100 kilopascal. After setting the sigma 3, which is the chamber pressure, to 100 kilopascals, we are going to create that pressure inside the triaxial chamber by using this constant pressure unit. We are going to use this comparator watch, which is mounted on the constant pressure unit. We are going to open to the outlet valve, and then we are going to open just one valve on the chamber. We are going to increase pressure to 100 kilopascal slowly by using this knob. As you can see, it is 90. Yes, it It is 100 kilopascal. We are waiting to equilibrium. It is 100 kilopascal. After 100 kilopascal is in equilibrium is maintained, we are going to open this valve to let the pressure go inside the triaxial chamber. And wait for a while to just pressure to be stabilized. And now we are going to initiate the test. As you can see on the TFT screen, we have previously determined speed of 1 millimeters per minute. And we are going to initiate the test using the software. And the machine is going to hire the lower platen with the determined speed. Now on the program, we are going to press just the start button and the test will be initiated. As you can see, load and flow values, which is the axial displacement, is increasing, and axial strain in percentage and the deviatoric stress is automatically calculated by the program. And the more circles is going to be drawn by the program automatically again. On this graph you can see the load and flow values live. As you can see, the test has initiated and we are going to wait until the shearing process is done, which may take 10 to 30 minutes, and we are going to wait until the shearing operation is done. Now let's see test software, which is designed specially to conduct CU and CD experiments. This is the program. On the very right side you see the help tab, and next to it there is a language tab, and there is a calibration menu which allows you to calibrate pressure transducers and LVDT devices. And file analyze. This is for the previous data files to be analyzed. And the very important one is the file test. We are creating a TXT file. We have on here up to 4 different specimen types. Since we are doing with the first specimen, we are choosing specimen number A. And on here, current test stage and previous test stages are 0 because we haven't started the test yet. Now we are going to connect the data logger to the pressure transducers by using these connection cables. The first channel is for cell pressure, therefore it is going to be connected to the cell pressure transducer. And second channel is for pore pressure measurement. Therefore, second connection cable is going to be connected to the pore pressure transducer. And finally, the third channel is for back pressure transducer. And the third cable is going to be connected to the back pressure transducer. Okay, on the screen we are seeing some meaningless values because it is just connected, and it is also calibrated. Therefore we are going to just reset the initial values. The axial displacement and the force is going to be reset on the TFT screen here. We are two buttons on the test screen. One of them is tear load, which resets the load, and tear displacement, which resets the displacement, I mean the LVDT reading values over here. Now they are all set to 0, and we are ready to start the test. Now on the test screen we are going to create a new test file. Let's say consolidated undrained. And after creating this file, we are going to click on the test button. Now we have here a newly opened button which writes test initialize. We are clicking on it. We are choosing the test type over here, consolidated undrained. Let's say job number 1, company name test, you can write anything. Project X, location Ankara, borehole ID, sample depth, and the date. On the boxes in the middle part of the program, we have diameter, height, initial area, volume, sample weight, and bulk density. Since we have prepared 50 millimeters of specimen, we are going to write 50 millimeters as the specimen diameter. As you can see, the area is automatically calculated. We have 100 millimeters of specimen height. We have entered 100 millimeters, and therefore the volume also calculated automatically. And before the test, we have measured our specimen as 260 grams, and we are entering it here. And the bulk density is also calculated as 1.32. On the right side of the boxes, we have an option to choose the drainage, where the drainage is going to be done. Since our drainage and back pressure unit is connected to the top, we have selected the top part. Since we have no side drains, we are not clicking this box, and that's it. Now we are clicking the test button again, and as you can see, we have two other boxes opened over here. One of them is test saturation cell pressure increment, and the second one is test saturation back pressure increment. Now, before continuing the test, we should operate our constant pressure units. Now let's initiate our constant pressure units. Since the pressure arranging knobs initially on the very counterclockwise direction, the initial pressure is 0. Now we are going to increase the pressure on the chamber, inside of the chamber, to 50 kilopascals, because we have selected 50 kilopascals of chamber pressure increments. Now we are going to open this valve on the constant pressure unit, which is connected to here, cell pressure outlet. We are just opening the outermost valve. We are not going to open this valve yet. Now we are going to arrange the pressure to 50 kilopascals while using this knob. And we are going to also check the pressure increasing on the computer screen at the very upper left side. As you can see, it's 43, 45, 6, 47. Oops. And now it is around 50 kilopascals. Now this, we are on the program now. We are clicking on the test saturation cell pressure increment. And again clicking continue. And after I press the start test countdown, the software is going to start counting down. As well as I see the 0 on the screen, I'm going to open the valve to let the pressure inside to the chamber. Two, 1, and I open the pressure, and now chamber pressure is increasing. I arrange the pressure here while using this pressure transducer without opening the inside valve, and simultaneously, after finishing the countdown, I open the inside valve to let the pressure go and affect the specimen inside the chamber. Now, as you can see from the computer screen, the pressure is going to be equilibrated. Now we are going to move on to the second stage by ending this stage. I'm clicking to end test stage and test again. Now I'm going to click the test saturation back pressure increment, which I'm going to do the same pressure, same procedure to the back pressure, which is inside to the specimen. Now I'm going to arrange the pore pressures again. With this constant, I'm again opening the valve of the constant pressure unit, which is connected to the volume change, and then connected to the back pressure from the top cap. Now the important thing is we should arrange this knob before starting increasing the pressure. We are going to choose flow up because our piston is at the very bottom. And then we are going to open the outer valve on the pore pressure line, back pressure line, I'm sorry, and I'm going to keep this inner valve closed. Now I'm going to increase the pressure to 40 kilopascals because we have, in the beginning of the test, we have chosen 10 kilopascals of pressure differential between chamber pressure and back pressure, which means we have arranged the cell pressure as 50 kilopascals, and now we are going to arrange this one to 40, which makes 10 kilopascals of differential difference. Now, as you can see from here, as I move this knob, as I increase the pressure, the back pressure on the computer screen is going to increase. For example, we have exceeded the 40 kilopascal on the back pressure side over here, but since we didn't open the inner valve, we are on the safe side. We are now reducing the pressure to around 40 kilopascals. Now after the arrangement, we are going to open the inner valve again and letting the 40 kilopascal pressure go inside to the specimen from the back pressure side, which on the top cap. Now we are going to wait for the pore pressure to be stabilized. After the pore pressure stabilization, we are going to go to another pressure increment to the test saturation cell pressure again, the middle one. Now I'm going to increase the pressure by closing this inner valve again. I'm closing this valve. And another increment of 50, which makes 100 kilopascal, is going to be applied inside to the cell. As you can see the increase on the test screen. It is around 100 kilopascals, and again I am going to click to the continue button, and it will ask for the countdown again, and the countdown stops. As well as the countdown stops, I'm going to open this valve now and letting the 100 kilopascals go inside to the chamber. And now, since we have 10 kilopascals of pressure difference between cell pressure and back pressure, we are going to increase the back pressure to 90 kilopascals. In order to do that, now we are going to close again the inner valve on the back pressure unit and increase the pressure while using this knob. As you can see on the test screen, it is a little bit reached of 90. Yes, it's now around 90 kilopascals. Now we are going to open the inside valve and letting the pore pressure go inside to the specimen. Actually, this pressure is this procedure is called saturation phase, which is going to be followed by the consolidation phase, and these cell pressure increasing and back pressure increasing step by step, they will go until the B value is reached to the, let's say, in some standards it's 95%. And we are checking here the calculation of the B value. program calculates the B value automatically, and this is now on 0.79. We have to reach 0.95 in order to say that the saturation is completed. It is now 81%, and we are waiting for pore pressure readings to stabilize. After pore pressure readings are stabilized, let's say after 1 minute, the change is less than 5%, we can go to another cell pressure and back pressure increasing step. Let's assume that our B value is go to the 95%, and now we can go to the consolidation process. Now we have calculated the B value, Skempton's B value. After the saturation process, which determined by the Skempton's B value, is complete, now we can go forward to do consolidation process. To do that, we are going to choose test consolidation button from the software and follow the instructions simply. On the cell pressure device, we are going to arrange the cell pressure to 290 kilopascals. It is because we have 90 kilopascals of back pressure inside the specimen, and our predetermined effective consolidation stress is 200 kilopascals. In order to supply at 200 kilopascals of effective consolidation stress, 200 plus 90 kilopascals gives us 290 kilopascals of cell pressure requirement. Now we are going to close the inside valve of the cell pressure inlet, and we are going to arrange the cell pressure to 290 kilopascals. On the test screen, you can see the increase on the cell pressure. But we didn't apply this stress inside to the cell yet. Cell pressure is set to 290 kilopascals. We are going to click the continue button, and we are going to press this test countdown, and as the countdown stops, we are going to open the cell pressure valve slowly. 3, 2, 1, and we are opening it. Now we have increased the cell pressure to 290 kilopascals. We are going to wait a little bit to pressure values to be equilibrated. And after the countdown, we can see that the volume change measurements will be reset at 0 automatically. This process may go a little bit longer, and we are going to wait until the consolidation process is complete, and we are going to measure the volume of water which goes outside from inside of the specimen with the volume change device. And according to the volume change, we are going to calculate the shearing speed. Completed the consolidation process, And the last stage is the shearing stage, which is written as compression in CU on the software. We are going to follow these instructions again. These instructions are according to the standards. Now first we are going to close the back pressure valve. And we are going to enter a speed. As you can see from the volume change, we have 3.52 milliliters of water that has go outside from the specimen. According to that speed, there is a suggested rate in millimeters per minute, which is 0.0002, and we are going to enter that value into the rate that will be used, 30 and 2. This is the compression rate which the multiplex machine is going to move the lower platen upside. And then we are going to reset the force and reset axial displacement. And we are going to start the process of shearing. Now we are going to click the continue button and start test, and it will count down and start the compression. As you can see, or maybe here, our multiplex device has started the compression and shearing process, which may take quite a long time because the rate is very low. And we are going to wait until the pressure is done. Now, as you can see from here on the test screen, as the displacement increases, the stress versus displacement graphic will be drawn onto this screen. And after the 10% of axial displacement strain, the program will automatically detect the failure and stop the process and give the results to the software program. Now our test has been finished. The shearing process is done. As you can see over here, there is a straight shearing plane after the compression, and our specimen has been deformed. We can collect the more circles for UU test and the maximum stress values, load values, and etc. from our software, and then we can do related calculations or present it as the related format. And this is the end of our experiments. Have a good day.